Good evening, everyone. Thank you for joining us tonight for our Caltech Astronomy Stargazing Lecture. My name is Dr. Cameron Hummels. I'll be your host for this evening's event. We host these events once a month on Friday nights like tonight and have been doing so for the last 6.5 years. Almost all of them have been recorded and placed on YouTube. We're actually live streaming right now to YouTube, so we'll, during the Q&A session, take questions from the online audience as well as the in-person audience. But that also means that these lectures, including tonight, will be available kind of in perpetuity if you go onto YouTube and look up the Caltech Astronomy Outreach page. So the schedule for tonight, normally we accompany these with stargazing with telescopes on the fields just behind us. As you probably saw when you arrived, there's quite a bit of cloud cover overhead, and sadly, optical observational astronomy has not yet reached a point where we can see through those clouds from here on Earth, although there have been many attempts to forego and try this. So we probably won't have the observing component after the presentation, but as a rough schedule of how tonight's going to go, in a few moments I'll introduce our speaker, who will give roughly 30 minutes presentation on the dawn of the universe, the search for cosmic dawn and early galaxy evolution studies. So after that 30 minutes, we'll take a brief Q&A with all of you here in the audience and perhaps some of the people online as well. And then after 5 or 10 minutes, we'll kind of transfer into a Q&A panel consisting of our speaker, myself, and a few other members of the department who work on different areas of astrophysics. And then we'll be happy to take additional questions from all of you on not just the content of the presentation, although definitely that, but any questions you might have, maybe something you read in the news about astronomy, or something that you've wondered for a long time about space science and physics. So we're happy to do that for the rest of the evening. Some of you may have seen on the way in, we have a spectroscope set up with a compact fluorescent light bulb, so you can really see some of the techniques that Professor Ellis is going to be talking about that we utilize to better understand the nature of objects on the other side of the universe. So that'll continue to be operated kind of throughout the program. So on your way out, you could potentially look through that if you didn't get a chance already. In addition to these events, we have a sister series of events called Astronomy on Tap. Those take place at a restaurant bar in Old Town, Pasadena, just a couple miles east of us, at a place called the Dog House Beer Garden. Pretty good food. And we host those one Monday night a month. Our last one was actually just this week. We hosted the chief engineer from JPL, Rob Manning, and Shannon Statham, an aerospace engineer from JPL. And the next one of those will be, I think, May 15th, where we're going to have two scientists, one from JPL and one from Caltech, talking about large-scale structure in the universe, like the distribution of galaxies, but also just matter on large-scale structures in our universe, which should be pretty exciting. Other announcements, I think those are all of my major announcements. So our speaker tonight is quite special. And normally I don't write down a bunch of stuff for the introduction, but I had to because he's had such a long and prominent career in the field of astrophysics in a variety of different research topics. But he's most known in the field of observational cosmology, studying the universe using observations from telescopes, and galaxy formation and evolution that he's going to talk to us tonight about. So Richard Ellis got his start at University College London about 50 years ago, and did his PhD at Oxford before he took a number of positions over the intervening few decades. For a while, he was faculty at University of Durham, and he worked at the Royal Greenwich Observatory just outside of London. Then he was the Plumian professor at Cambridge for a few years, which is a highly esteemed position in the field of astrophysics, before he came to Caltech, and he was with us for 16 years, from 1999 to 2015. And then during that period, he was the director of Palomar Observatory, which you may be familiar with. For a long time, it was the largest telescope in the world, just south of here, near San Diego. And then he had a brief stint at the European Southern Observatory before he rejoined University College London, where he got his start nearly 50 years ago. So that's kind of his trajectory, but along that path, he's made numerous contributions to the field of astrophysics in various different areas, including, as I said, galaxy formation and evolution and observational cosmology, stellar astrophysics, astronomical instrumentation, like the development of multi-object spectrographs and the prime focus spectrograph that's aboard the Subaru telescope right now. He's done work on the accelerating expansion of the universe. He was involved in the supernova cosmology project that was awarded the Nobel Prize in 2011, I think. He's done work with gravitational lensing and large-scale structure, involved with the 2DF galaxy redshift survey, reionization, and he was actually the PI of the Hubble Ultra Deep Field. If you're familiar with that image, a lot of people will showcase it as like the most distant image that we've ever seen. And in fact, and it's right here, but this is the JW version. Yeah. But yeah, this is the JW view of that same field, isn't it? Oh, forgive me. Okay, thank you for the correction. I'm sorry, I'm just about done. In addition to all of his numerous accolades and awards, just 2 days ago it was announced that he was awarded the Gruber Prize in Cosmology, which is kind of like the Nobel Prize in Cosmology, and it comes with it a lot of prestige and a very large award. So, and along with all of this, he just wrote a book a few months ago. It's now out, and we didn't have it available to sell tonight, but we do have a discount code that'll be worth 30% off the overall price of the book. The book is called When Galaxies Were Born, The Quest for Cosmic Dawn. And I've got a link on the YouTube description and on our website. If you go to the website, that links to the Princeton publisher where you can buy it. And the code is Ellis30, ELLIS 30. And that's also linked on the YouTube description. So with all of those accolades, please welcome Dr. Richard Ellis.
Thank you. Okay, thank you very much. Thank you very much for coming tonight. Thank you all of those online. It's very nice to be back at Caltech again. I was here, as Cameron said, for 16 years, and I miss it greatly, but I am now in London. It is an amazing time in astronomy because of the launch and success of the James Webb Space Telescope. So how many people watched the launch of James Webb on Christmas Day 2021? Yeah, you see, excellent. My heart was in my mouth because so many things could have gone wrong, but thankfully it's a really happy story. It's been a huge success, and I'm going to tell you how it's transforming our view of the universe. This image, which I had to correct Cameron, is actually the first deep public image that was revealed from the White House in July of last year. It is a cluster of galaxies. Well, obviously there's a bright star from the Milky Way in the center here, but that's not really of interest. All of these white objects here are galaxies that are at the same distance. They're physically associated in what we call a cluster of galaxies. And even that's not what's particularly interesting. What's more interesting is all the objects behind, which are red. And as you can see, many of them are stretched and distorted. And this is a phenomenon which we call gravitational lensing. The light from these galaxies, which are much further away than the white cluster galaxies, are being distorted and bent by the gravity, the mass of this cluster of galaxies. And it gives us a view of the distant universe that is magnified by this cluster of galaxies. Now, I think it's fair to say that when President Biden introduced this image, he didn't fully grasp the physics of what was going on in this image, but we'll let him, we'll excuse him for that because he had other things on his mind at the time. But it is a very striking image, and this began the science operation of the James Webb Space Telescope last July. Now, why, you might ask, do we want to see deep in the universe? And the answer is that the universe, believe me, is an enormous place. and light travels at a fixed speed. So when we look to great distances, we look back in time. When we look at the sun, we see the sun as it was 8 minutes ago. That's how long a light ray takes to reach the Earth from the sun. When we look at the nearest star, it's 4 years away. We see it as it was 4 years ago. But the situation is very different when we use a big telescope like the Hubble or the James Webb Space Telescope. We see not 1 million years back in time, not even 1 billion years back in time, but as long as over 13 billion years in the past. So astronomers are like time travelers. They can actually witness directly the history of the universe by looking with powerful telescopes further and further in distance. And so we use the phrase look back time to determine how far back in time we're seeing an individual galaxy. So the question arises how, when we take a picture, there are galaxies obviously at various distances, and we need a marker, we need some sort of measurement for each galaxy of how far back we're looking in distance and hence time. And the reason we can do this is very, very handy fact, and that is that the universe is expanding. Now you probably know, you've probably heard about the expansion of the universe, and you may have wondered about what's going on. It's incorrect to think of the expansion of the universe as galaxies moving as projectiles shot out of the Big Bang into pre-existing space. That is not the correct picture. It is space itself that is being stretched. And I know it's a difficult concept to imagine space. We all think of space as something empty, you know, but in fact, the space itself is being stretched. So for example, in this slide here, if you focus, I hope those of you online can see my little curious pointer here. Here's a galaxy, and we're over here on the left, and a light ray, a blue light ray, leaves this galaxy on its journey to the Earth. And because light is a fixed speed, it doesn't reach us instantly, it's traveling towards us. And in the time it takes to reach us, space is stretched. And by the time it reaches us, not only has the distance between that galaxy and the Earth increased dramatically, but also the wavelength of the light itself has been stretched. It's been shifted from a blue light ray to a red light ray. And that's what we call the redshift. You've probably heard of the term redshift. This is the only equation, incidentally, in my book, and you don't need it anyway. You can just look at this picture and you can see that the redshift, that is the stretching of light rays, is a measure of the factor by which the universe has expanded since the light left that galaxy. So it's a time marker. So when we take a picture of the deep universe, you can think of it as a time tunnel, galaxies at all these different distances. And if we can measure the redshifts of each of these galaxies, we know at which epoch in history we're observing it. We need a picture, we need an understanding of how the universe is expanding to do that, but we can discuss that maybe in the Q&A. We have a pretty good understanding of the rate at which the universe is expanding at different times in its history, so that we can convert this measurement of the stretching of light into the look-back time. And the universe, as I said, is 13.8 billion years old. That's about 3 times older than the solar system. And so, you know, the galaxies that we're looking at, you know, we're seeing them as they were before the Earth was in existence, and in some cases, all the way back to when the universe was in its infancy. So we have this trick. It's a little bit like geology, where you see the history of the layers of the Earth, you know, and how they were created over the lifetime of the Earth. But this time, we're talking about the history of the universe. So my colleagues and I and many others have championed this beautiful fact that we can witness directly the past using the Hubble and ground-based telescopes. And this is largely contained in the story in my book. So today, we generally find 2 kinds of galaxies. We see galaxies like this one on the right here, which is called an elliptical galaxy. It's a ball of stars, and all of those stars are the same color, more or less. We think that's because it formed a long, long time ago, and it's very, very old, and the stars themselves are very old. Then there's a galaxy like this one, which is a spiral galaxy. You can see it's got a nucleus. It's got beautiful spiral arms. Our Milky Way itself is very similar to this kind of galaxy. If we go back to when the universe was only 5 billion years old, you can see there are galaxies that resemble the elliptical galaxy, like this pair on the left here. There are galaxies in the center panel there that look like spiral galaxies. They're not perhaps as elegant or as well formed, but they do have blue disks-like structures, and they have a nucleus, just like that beautiful spiral nearby. But when we go back to when the universe was only 1 to 2 billion years old, you can see the galaxies don't have any symmetry at all. They don't look like anything like the galaxies that we see today. Many of them have multiple components, as if they're coalescing. Many of them are irregular in shape, like this one here, and they're physically small as well. So I'm not saying this whole picture has been sorted out yet, but broadly speaking, over 90% of the history of the universe, we've got a general picture of how galaxies assemble, they merge, and they settle down, and they end up with these beautiful regular structures. But the theme of tonight's talk and my book is to go right back to when the universe was dark and the first galaxies emerged from darkness. And we call the moment where galaxies and stars first began to shine in the universe cosmic dawn. This obviously is a cartoon. Time is running from left to right. The universe began with a big bang, and the universe started expanding at that time. And as the universe expanded, it cooled. It was initially just a huge plasma of gas and particles, and light rays were being scattered around within this plasma. And then as the plasma cooled, eventually the hydrogen atom formed for the first time. And at that point, this glow from the Big Bang was able to permeate. But apart from that glow from the Big Bang, there were no stars or galaxies. We call this period the Dark Ages. Now, astronomers are very fond of the adjective dark. You've probably heard of dark matter. You've probably heard of dark energy, Dark Ages. It's really good. It adds an air of mystery to the subject, which is extremely good for raising funding for projects in astronomy. Okay, so what happened then? Well, these dark hydrogen clouds, they clump under gravity. Gravity is an attractive force. It brings together the clouds of gas. Those clouds of gas eventually collapse, and as they collapse, they get hot, just like a bicycle tire gets warm when you pump it up and you compress the air inside it. And as that gas gets hotter and hotter, it eventually ignites nuclear fusion. And that's the reason the sun is shining. The sun is a nuclear fusion reactor that's converting hydrogen into helium, and the mass loss from that conversion leads to energy that makes up you and me and everything that we see around us. So it must have been an amazing moment when out of darkness, suddenly there was starlight. Now, I know you're going to ask me questions about the Big Bang and what came before it, but if you could just imagine for a moment that cosmic dawn is just as important as the Big Bang. Why is that? Well, because the elements that we see around us were all made in stars. Apart from hydrogen and a little bit of helium, there was nothing else in these first stars. No calcium, no carbon, no oxygen, no nitrogen, no iron, no silicon. All of that, all of the chemistry that we see around us, everything in this room was synthesized in stars. All the atoms in our body, all the nuclei, the calcium in our bones, the iron in our blood, everything was made in stars. Okay, so cosmic dawn is the beginning of you and me. So in a sense, it's our origin. It's just as important as the Big Bang itself. So my book traces the history from when I was an undergraduate, which is a long time ago, in the late 1960s. And this is the most distant object that had ever been seen as a function of the date of the publication. And you can see that in the 1960s, galaxies had very, very low redshift. The so-called redshift record, the most distant object known, was very, very low. But as I've lived through an amazing time where we've made enormous progress in moving to when detecting galaxies when the universe was only a few 100 million years old, 3%, 4%, 5% of its present age. And I showed this slide very often in my public talks. As recently as May of last year, it's already out of date. In 6 months, only 6 months with the James Webb Space Telescope, we've revolutionized our understanding of this frontier, the so-called frontier. So what are the questions? What are we asking now? Where are we now? What kind of questions are we posing for this amazing telescope? One, when did cosmic dawn occur? Was it a gradual event? Did it occur over a couple of 100 million years? Or was it a sudden event? Did the universe switch on, you know? And most importantly, will we recognize a baby galaxy that's emerging from darkness? How will we determine what we call the first generation system that emerges from darkness? Will we recognize such an object with the James Webb Space Telescope? So, you know, my book is semi-autobiographical. It starts, the story of looking back in time starts at the Palomar Observatory. How many people have been to Mount Palomar? I recommend you go. It's the visitor center is now open. It's a beautiful mountain. It's a 2-hour drive from here. And it's a very, very famous observatory that's still in full operation, as you can see over there on the right. My career began in Australia. The UK teamed up with the Australians to build a telescope in the 1970s. It was opened by Prince Charles when he was a young man, now King Charles III, in Australia. The UK then built a telescope in the Canary Islands, very beautiful place, the William Herschel telescope. As Cameron said, I moved to California in 1999 because of the mighty Keck telescopes in Hawaii. And then recently back in Europe, I've been using the European Observatory in the Atacama Desert in Chile. Now, these are all ground-based telescopes, and the power of these telescopes is governed by the diameter of the main mirror. That is the power of the telescope. It increases as the square of the diameter of those mirrors. But of course, there are space telescopes too. So Hubble, everybody's heard of Hubble. By the way, it's not eclipsed in any way by James Webb. Hubble is an optical telescope. James Webb is an infrared telescope. If anything, James Webb is eclipsed the Spitzer Space Telescope, which of course was operated out of Pasadena, and it's now finished its survey. It was a modest telescope, as you can see, 85 centimeters. James Webb is a monster by comparison and much more powerful. So we start this story at Palomar with this gentleman here, George Ellery Hale. He was a very eminent solar astronomer. He lived in Pasadena. You can see his house. It's very within walking distance of here. And he built a little observatory there. And he's very famous because he raised the funds. He was extremely good at getting money out of wealthy donors. And he managed to fund successively the 3 largest telescopes in the world, which you can still see, the 60-inch and the 100-inch at Mount Wilson, and then the majestic 200-inch at Palomar, which sadly he never lived to see to completion because he died in 1938. When I was an 8-year-old boy, I had an encyclopedia, and in that encyclopedia was this picture of a cutout of an observatory. It didn't tell me where this observatory was, but as a boy, I would flip through the encyclopedia and come back to this page time after time. And it's obviously, as you can see, the Palomar 200-inch. And little did I know when I was 8 years old that I would one day become here and be the director of that observatory. So George Ellery Hale hired this guy, Edwin Hubble, whose name, of course, graces the Space Telescope. He set out to find distant galaxies. He knew that we were looking back in time, but he wanted to measure the rate at which the universe was slowing down in its expansion. And the trick he was using was he would use the brightness of the galaxy to estimate the distance, and then he would measure the redshift, which told him the rate at which the universe was expanding at that time. And by comparing the expansion rate of the universe in the past with the expansion rate today, he hoped to determine whether the universe was slowing down, and if so, was it slowing down sufficiently that it would eventually stop expanding. Sadly, he had a heart attack. He lived very close, actually, to here, and he had a heart attack in his driveway and died in 1953. So he never really used the 200-inch successfully for this project, because that telescope only came online in 1948. So he handed the baton to his disciple, Alan Sandage, who died about 10 years ago, who took over the mantle of using the 200-inch to do this. Now, in a statistic that would amaze astronomers today, this was the biggest telescope in the world, and there was only Alan Sandage. He had so much access to it to do this big project. But at that time, Caltech set up an astronomy department, and a young upstart, Jim Gunn, decided that he too could do this project. So here in Pasadena, you had two rival teams using the same telescope to try to do the same project. And it was if you go through the literature, it's a very, very exciting history, which I discuss briefly in my book. But then along came this woman, Beatrice Tinsley, a New Zealander, a theorist, and she pointed out to Jim Gunn and Sandage that this experiment was futile, because galaxies, you can't estimate the distance to a galaxy by its brightness. Galaxies change their brightnesses with time. Just as stars evolve and explode, so galaxies are made of stars, and they must evolve too. So when you look back in time, you can't estimate the distance of a galaxy by its brightness or luminosity. And so there was, when I was a postdoc in the late 70s, there was a huge paradigm shift in the subject from using galaxies as traces of the expansion of the universe to looking to their evolution and ultimately to get to cosmic dawn. And it was assisted by a number of revolutions. So the reason that curve of the most distant galaxy races up so fast after the 1970s and 80s is because of three reasons. Number one, digital detectors. Sandage and Gunn were using, and Hubble were using the good old photographic plate to measure, to detect the galaxies and measure their redshifts. And along came the digital detector, the charge-coupled device invented in the late 70s and put on telescopes in the 80s. The detectors you have in your iPhones, are 30 to 40 times more sensitive than the photographic plate. So overnight, these telescopes suddenly became much more powerful. And now we have big mosaics of these detectors. This is a Japanese mosaic of many individual charged-coupled devices, which is an 870 megapixel camera. You can take an entire picture of the famous Andromeda spiral. We built bigger telescopes. The 200-inch, sadly, no longer became the biggest telescope in the early 90s. There's the twin Keck telescopes with 10-meter mirror, the Gemini telescopes, the European Southern Observatory, and so forth. And then finally, we developed multi-object spectroscopy. Sandage and Gunn were measuring the redshifts of these galaxies one by one, often with exposures of a single whole night on the telescope. And along came optical fibers. So what we're doing here is we're making a brass plate and we're drilling holes at the positions of all the galaxies in the field of view and plugging an optical fiber into a hole in the plate so that we can measure the spectra. We can gather the signal from each galaxy with this optical fiber and measure not one galaxy, but 50 at a time. And obviously that transforms the situation. Now, it started out very primitively. This is me and a colleague. Each fiber has a number and each hole has a number, and you manually plug the fiber into the hole and you have a little piece of paper with which fiber number goes in which hole number. And woe betide you if lose that piece of paper, because otherwise you won't have any idea what you've been observing. So we eventually started to automate this with robotics. So what you see here is the light is coming down from above, and there's a tiny right-angle prism that sends the light into this fiber. And then this magnet comes along and moves all of these little units to the positions of the galaxies. And rather as a publicity stunt, we use this to make a picture of a map of Australia, to which the usual response was, "What about Tasmania?" I want to introduce an idea that one of my former colleagues here at Caltech pioneered, Chuck Steidel, that speeds up finding these early galaxies. Galaxies have a range of distances. If we're only interested in the very most distant that tell us about the universe when it's young, there's a very nice technique that's based on the idea that there's hydrogen in the universe. Now, there's not only hydrogen in stars and in the gas clouds in between the stars, but there's hydrogen even in between galaxies. And this hydrogen absorbs in the ultraviolet. And so if a galaxy is particularly distant, it can be visible in the red filter with that little circle, the blue circle there. It's visible in the green filter, and then notice it disappears in the ultraviolet filter. And this is a telltale signal that the galaxy is very distant. So this was applied wholesale with Hubble. These are all the color filters on Hubble, ordered by wavelength. There are blue filters, green filters, orange filters, red filters, and infrared filters. And here's a galaxy. This is simulated, obviously, but as the redshift increases, the galaxy disappears in progressively longer filters. So if the redshift is small, it disappears in the blue filter. If the galaxy is very distant, it's redshifted, and hydrogen absorption cuts it off in the infrared filter. Now, I want you to remember, this is probably important, because we call this an approximate redshift. It's not a very accurate redshift, but it gives us a head start in determining which objects are the most distant. And we call this photometric redshifts. So let's have a little interlude just for a minute. What's it like to go to one of these big telescopes? Well, I'm afraid I am a romantic. I like going to the telescope. Of course, it is possible to now observe on the internet, but then, observing just becomes like another day in the office, and it's not very exciting to me. I really like to go to the remote mountaintop, stand on the mountaintop, watch the sunset, and think of, what discoveries I might make that night. It's inspirational for students. This right guy here is one of my former students. He's controlling the biggest telescope in the world. I mean, that's an aspiration that many people have when they're at school. And of course, if you make a discovery in real time, it's actually amazing. But unfortunately, there are cloudy nights. Now, you don't get a rain check. You don't get a rain check on a big telescope. Every night is allocated to somebody. So if it's cloudy, you fly all the way to Chile or Hawaii, and it's cloudy, it's just your tough luck. This is a cloudy night photograph. And this guy here on the right, these are former students. He's very happy because he's finished his thesis, He is not affected by any of this. This guy here is Italian. I don't know, the Italians are always happy. They never seem to, have any problems at all, okay. This guy here his thesis is going down the drain. This is the fourth cloudy night in a row, and you can see he's pretty forlorn. So my job as the professor is to buy the pizza the bottles of wine, and I think that's why this photograph is slightly blurred. So how deep did we reach with Hubble? Well, there's two techniques. One is to steer Hubble into a not particularly interesting area of sky and expose for a long time. And this is the image that Cameron mentioned, the ultra-deep field, which we took in 2012. It was a collaboration between myself and Jim Dunlop, who's professor at Edinburgh. This is taken at Edinburgh Royal Observatory in Edinburgh. This is the image. It still is the deepest Hubble image. It's about 2 weeks of exposure. The area of sky is about 1/10 of the diameter of the full moon, and there's about 3,000 galaxies in here. And the most distant ones you probably can't see, but these colored circles are the most distant ones, and the most distant of all is circled in yellow there. And we thought, but we were very nervous in 2012, whether this galaxy really was at a redshift of 11.9. It was selected by this filter technique. We didn't get a spectrum of it at all. I'm going to come back to that object with James Webb in a moment. The other technique, I told you there were two techniques, is to use the same technique in that Joe Biden picture where I started my lecture. You look through a cluster of galaxies. It acts as a giant magnifying glass in space. It's a free telephoto lens. You look through this cluster and you magnify distant objects. And it gives you a little additional boost compared to pointing in a blank area of sky. Now, these two techniques were used to do a census of galaxies at different look-back times. So what you see here is the number of galaxies, strictly the number density of galaxies, against redshift, or if you prefer, time from the Big Bang is moving from right to left. And for the aficionados, this is what we call a logarithmic scale. So from top to bottom is a change of 1,000, okay? So at a redshift of 2, to the limit of Hubble, the number of galaxies are declining. Well, that's good news. So you would imagine when we run out of galaxies, that must be cosmic dawn. But unfortunately, there was a discussion in the literature, as to whether it's falling steeply like this, or whether there's, you can see that different observers had different estimates. And that's where the subject lay until last year. And once again, this is now out of date. And the result, I'll show you in a minute, is very surprising. There is one other technique for trying to pinpoint cosmic dawn, and that's not to directly witness the numbers as they go down to 0, but to measure the stellar ages of some of the most distant galaxies. So the analogy I like to use here is you walk down the street and you see a little boy. And if you know the age of that boy, say he's 4 years old, then you know exactly when he was born. Likewise, we go as far as we can with Hubble, and we find some galaxies like this one here at a redshift of 9, and we do our best to see how old it is. And that allows us to look a little bit further than Hubble can actually see to try to determine when that galaxy was born. And that's what we did. We did this when I had left Caltech. We did it in London. We went to the Atacama Desert. There it is in the top left there. No trees, nothing, just desert. In some parts of the Atacama Desert, it's never rained in recorded history. This is the galaxy up here. This is us in front of the Very Large Telescope in Chile. You've got to hand it to the Europeans. This is the only big observatory with a swimming pool. You've got to have your luxury when you're a European. We found that this galaxy is 290 million years old at a redshift of 9. And that means that it formed when the universe was only 250 million years old, an epoch we could not see directly with Hubble. And we did this for 6 galaxies in total. So just before the launch of James Webb, we predicted that cosmic dawn would be somewhere between 250 and 400 million years after the Big Bang, an epoch that's within reach of James Webb. So I finally come to this amazing telescope. And just before lockdown, I was here in this room giving a talk for the end of the Spitzer Space Telescope. And I was privileged to go to El Segundo, to Northrop Grumman, to see James Webb in person, as it were. There's a human here. So it gives you some idea of the size of this monster. Seeing this thing is like a religious experience. You know, it's 6.5 meters. There's 16 segments. They're made of beryllium, which is the lightest metal. They're gold-coated, very, very thin layer of gold. And of course, a very expensive facility, $10 billion. I was the only European on the committee in 1996 that proposed this telescope. 1996 to 2021, 25 years to build this thing. 1,000 engineers working on this for 25 years. Cameron mentioned Durham. I was at Durham University. It's a very famous city in England. It has a monster cathedral that was built in 1050 or something. And you know, the history of those cathedrals, entire populations of builders, you know, and stonemasons would move with their families to where the cathedral was being built. And they would live there for 50 years, building this cathedral. It was a generational thing. And that's what this is. This is like a cathedral. 25 years of people's careers building this monster. So imagine imagine how nervous you are when it's hanging by a hook, you know, about to be put in the nose cone of this Ariane space rocket. And then on Christmas Day, launched, and that's the last view of it. We won't see it because it's not accessible. Unlike Hubble, there's no shuttle. It's not even orbiting the Earth, it's orbiting the sun. At a special point, where the gravity of the Earth and the sun equals the gravity that the Earth feels from the sun. So the two are always locked together, 1.5 million kilometers away. So here's where we are. This is the luminosity density again. There's that curve that was disputed. It is a curve that the theorists love, but it's not consistent with the data. You can see we see galaxies out now to redshifts of 13. There have been claims of galaxies out to redshift 16, well beyond Hubble. So the first good news is we were right. We predicted that there would be starlight beyond the horizon that was accessible to Hubble. But this curve is not going down as fast as the theory predicted. Now, what is this theory? Well, the theory is that stars are being formed out of gas with a constant rate of efficiency. And that curve actually fits remarkably well. I go back. Fits remarkably well the data. You can see up at the top here, this curve, it's called halo evolution. It fits very well the data at lower redshift, but it clearly falls apart in the new data with Hubble. The galaxies are too bright compared to theory, and we don't know why. So I'm going to leave that for the panel discussion. What are the possible explanations for that? Because I see Cameron's worried that I'm running out of time. Let me tell you that, remember those photometric redshifts were approximate. So one of the concerns has been, you know, these galaxies were all found by that color dropout technique. Remember that those filters moving, the things disappearing. How many of these objects are really at those distances? So the wonderful thing about James Webb is it has spectrographs. You will see spectrograph outside after the talk. The most distant object that we found in the Hubble data, thank goodness, since we put our money on it in 2012, has been confirmed. Here's the James Webb spectrum, and here's this dropout signal, and you can see it's a very beautiful spectrum. This morning, today, this is on the internet. So far, there have been over 70 papers on the internet on early galaxies with James Webb since last July. This is luminosity against redshift, and you can see the colored, the filled circles are all the galaxies that have been confirmed spectroscopically with James Webb. The rest are photometric redshifts using those color techniques. So we're slowly but surely confirming, and most of the redshifts that we found with the color technique have been verified. So you can see the relation is really very, very tight. All of this work in the last 6 months, I mean, it would have taken us decades to do this without James Webb. We can even measure the chemistry. Now, remember, I told you the chemistry was the beginning of cosmic dawn. So here's a spectrum of a galaxy. I never thought I would see this. You can see the signatures of nitrogen, helium, carbon, magnesium, oxygen, neon, when the universe was only 4 or 500 million years old. And of course, the trick now is to go back further. And the telltale signature of a baby galaxy would be that those elements are not yet had time to develop, because the stars are so young that they haven't processed the material and exploded as supernovae. So I'm going to end there and say the Holy Grail is, of course, this cosmic dawn. The key signature is going to be the absence of these elements like carbon, nitrogen, and oxygen. It's going to be challenging to do this, but I'm an optimist. James Webb is going to be there for 15 years. And over my career, all the telescopes that I've observed with, they all produced more science than was originally predicted when they were planned. So I like to say that unlike politicians, astronomers deliver far more than they predicted. Thank you very much.
We can take a few questions from the audience before we transition to the panel Q&A. Raise your hand and I'll hand the microphone to you so that our online audience can hear your question as well.
And do speak clearly, please, because I'm hard of hearing.
At the very end there, you're talking about the stars producing the heavier elements.
Right.
At what generation of stars would that be, do you think?
Okay. So stars have different masses. The most massive stars shine the brightest, as you would imagine, but they live in the fast lane and they burn out very quickly. And so they explode as supernovae, and all of the chemistry that they've produced is then sent into the gas that they formed from, and that is then available for the next generation of stars. So this period where the whole galaxy is pristine could be very, very short. It might only be 5 million years. Now, I know 5 million years is a long time for you and me, but believe me, in the early universe, it's a very short period. So finding a completely pristine system might be looking for a needle in a haystack. So my suggestion is going to be that we're going to do this statistically. We're probably going to measure the chemical composition of a sample of galaxies, maybe 20 or 30, and see how it declines as we go further back in time. I don't think we're going to wake up one day and say, gotcha, we've found a galaxy with no heavy elements in it. But it's a very narrow period of time, yeah.
Thank you. Thank you for the lecture. Your jokes
Can you speak up? I'm sorry.
Oh, yeah, your jokes were funny, but I also wanted to ask a little bit more clarification on the graph of luminosity versus redshift. So as Siri predicts, it's logarithmic, but what's observed is linear, what it looks like. So I wanted to ask questions of why. So redshift is influenced by how fast the universe is expanding, right?
The redshift is a measure of how much the universe has expanded since the light left that galaxy.
Okay.
Okay. So if you prefer, age of the universe is on the top, which is the easier way to look at this plot. And then this is the it's what we call a census. So it's the number of galaxies and all their luminosities added up. So it's the brightness of the universe in stars at that time.
The brightness
of all the stars in a given volume. Say you take a fixed volume of space.
Right,
okay.
But that's from the point of view of the Earth, or
well, it's what we observe.
Okay, so it's observed luminosity.
Yeah.
Okay,
yeah.
So could you go a little bit more into why there's a discrepancy, or why do you think there is a discrepancy?
Well, we're going to discuss that. As I said.
The panel.
Yeah, this is a big puzzle now. Why are these galaxies more luminous? How are they forming stars so prodigiously at these early times compared to what theory tells us?
Right.
Theory tells us that as we go back in time, there should be fewer and fewer galaxies, and if they form at a certain rate, then we should see that drop in the luminosity. But we don't. We see that the universe is more luminous at that early time than we predicted. So something new must be happening.
Interesting.
Yeah, very interesting. I've just been at a conference in Italy, and we spent all day discussing this. Yeah. This guy here, maybe?
Yeah.
We're going to come back to this in the panel, I'm sure.
Thank you for a really, really interesting lecture.
Thank you.
I had a question. So on the y-axis here, we're seeing the density per unit volume.
Yes.
And I'm curious how the variance changes with time. That is to say, how homogeneous are the galaxies, and is that matching expected theory?
Yeah. This is a very good question. And firstly, you remember this is just the beginning of James Webb data. And it may be that the areas of sky that we're studying are not typical. You know, the universe is clustered. So when we look at the sky, even in galaxy counts, as you saw, there are clusters of galaxies and so forth. So there's about 13 areas. This plot is made from about 13 different regions where James Webb has looked. And there are fluctuations. There's a couple of areas where there are 2 or 3 times more galaxies than we would have expected. So as the data improves, you know, these error bars will go down, that's for sure. But at the moment, they include that variance that you mentioned. Yeah.
Thank you.
Question. Yeah.
Additional questions from the audience? Yeah.
Thank you. Thank you very much, sir. It's sir, right? Not doctor. It would have to be the correct address. I have a very mundane, maybe naive question. This is a very big system. There's lots of targets, lots of observers. How do you distribute the observing time among the universe of competing astronomers?
Okay.
And do you operate as individuals? Do you have an individual
We have
hour
teams.
or two?
Yeah.
And what fraction of a day is the telescope actually gathering data?
Yeah. Okay. Well, the sociology of competing astronomers is a feature in my book. You know, if I can make a joke, but I will answer your question. Very recently in the London Times, they had your probably view of an astronomer is like an old man who goes up the mountain with an eyepiece and, you know, very calm and sits down and looks through the telescope, very, very serene and everything. Very recently, they had a ranking of the most stressful occupations, ranked by stress. And at the top were things like politician, stockbroker, you know, surgeon. And then way down the list was astronomer. It was below priest, you know, and this is just complete bullshit because it's just as competitive. And, you know, just as Sandage and Jim Gunn were competing, fighting over the 200-inch to get the glory of the expansion history of the universe. So since James Webb was launched, it's been madness. There are all these teams competing with one another. Now, how do we get data? Well, there's 2 ways. One is if you were lucky enough to build an instrument for James Webb, you get what is called guaranteed time. And that Those observations have been taken, but they're not publicly available. They're under wraps. So, those fortunate people, have fantastic data, but they're not sharing it with anybody else. The rest of us plebs have competed, directly through what is called guest observer time. And I've done very well. I got something like 300 hours of James Webb time, but the data is slowly coming in. It's not all in yet. And every year there's a call for proposals, and the competition is very fierce. So it is a highly competitive field. But fortunately, many people, including ourselves, have decided, we're such nice people, that we're going to make the data publicly available as it's observed. And that means that we've made all this progress. So pretty well everything I've talked about is from the public data sets that have been taken by the guest observers. The dreaded guaranteed time observers haven't really released much of their results yet, but we know they have fantastic data.
Sorry, I just wanted to add, I was gonna add to, if maybe they're interested, have you ever participated in that Gaia data competition on the release? They have a competition for data scientists, whoever can come up with a project to make sense of that data on the data release too from Gaia telescope. I thought if you're interested in competition.
Yeah. The sociology has moved, over my career, the sociology has moved from, a professor with 2 students, getting on a plane and going to the telescope and then coming back and writing a thesis and so on. Now the teams are 50 to 100 people. And, you need training to manage those kind of projects. How do you protect the careers of young people from being swamped by, professors who have more money and more resources to analyze the data faster? And how do you manage such a big team? So there's been a huge shift largely through these NASA facilities.
We'll take one last question before we transition to the Q&A. Any last question, or we can just transition? Yeah.
Hi, my question is about the equation you showed earlier, the relation between lambda and distance.
Yes.
I don't know much about astronomy. Just was curious how to get the lambda emit.
Okay, yeah. So I'm surprised nobody asked this. So the question is, how do we measure the redshift? I said you get a spectrograph. So if we go outside, you'll look through the eyepiece, you'll see that gas clouds emit in specific frequencies or wavelengths because of the energy levels in the atom. And we know those laboratory wavelengths very, very well over the last 200 years or so, through the work of very many famous astronomers, Fraunhofer and Niels Bohr and others. And so what we do is we get the spectrum of a distant galaxy and we recognize the pattern in these gas cloud lines and we relate them to the laboratory wavelengths. And that gives us the shift that's caused by the expansion of the universe. So if Cameron and his gang will take you in the break maybe, and you can have a look and see these sharp lines, and you would imagine now when you look at a distant galaxy, you see those same lines, but they've been redshifted. Yeah. Yeah. So right now we're going to transition to the Q&A panel, but if people want to check out, we're going to have like a 5-minute intermission as we get set up for it. I welcome you, particularly the woman who asked the question. So we have a spectroscope set up just out in the hallway that shows some of those lines for a compact fluorescent bulb, the bulbs that used to be used more frequently, but aren't so much now that we have LEDs. And so you can see specific emission lines that are these bright lines in different colors that are caused by the presence of certain elements like mercury or fluorine in the gas that's glowing. And it's the same thing with distant stars and galaxies. They're just shifted to different colors. So, well, let's all thank Professor Richard Ellis. Thank you. That was a wonderful presentation.
So as I said, we're going to set up. It'll take us about 5 minutes to set up. Sadly, it is still cloudy outside, so we won't be able to do any stargazing with the telescopes. If you need to take off, or if you want to just check things out, we also have a bathroom. You're free to go whenever you desire. But we're going to get started, and we'll have about an hour's worth of Q&A panel where we open it up to you guys and your questions, as well as our online audience. So stay tuned, and we'll get started. Oh, and the book. The book is now for sale. There's a link on YouTube. There's a link on the Caltech Astronomy website. It's not up here, but it's called. Yes, When Galaxies Were Born, The Quest for Cosmic Dawn. It came out a couple months ago, and there is a discount rate of 30%. It's only about a $30 book, so $25. So it's pretty affordable, and it goes through in much more deep depth the kind of content that Professor Ellis was discussing over the course of this presentation. Okay, we'll be back in just a second. Stressed as always. Here, I have a pen. I have my own pen. Oh, don't, you're fine. I just got cords all over the place. Have you read it? Yeah, it's a great read. Very interesting. It's very easy to read. Oh, that's kind of good. Yeah. Okay, Nick, here. Sorry, I put it wrong. No, of course not. No, you know, that's fine. Do I what? Yeah. You need a fifth chair for yourself? Yeah. You can see, D is on it. Thanks, D. Ananda, yes. It was a big table. Yeah, we were going to, and I was concerned about. Oh no, I thought it was one mile. No, you could walk. Do you feel that the romanticism has died? Yeah, you know, it's become a little bit, you know, I'm still a, you know, maybe it's because I'm old. Yes. I'm still Yeah. Yes, okay. Yeah, that was Isn't everything else in the almost 40 years over the other? Oh my God. Yeah. So I just thought my own that brought the book for him. Maybe we're together so we can. For the UK. No, sure. Yeah. The sociology. No, I'm a little bit exceptional. No, I don't like the big team. So I generally, when I was here, I really tried just to observe with the students, like in those photographs. But you know, it's getting. Maybe compete with a team of 50 people. Yes, we do. Yeah, once a year. Then there's a committee, a time allocation committee. Who's on the committee? It's you know, I've been on them. Oh, it's James Webb is about 5 times over 6.
So only 20%. Pretty tough. I did pretty well.
I was involved in I oversight committee.
Yes. Oh, you did? What's his name? Oh, yes. I know. I even know where you live. You lived in Orangeburg.
Were you there?
Well, I lived on West California Boulevard, and every time I passed to go and carry crossroad where the foot of the freeway is, you live in that house right opposite that thing. Somebody told me, oh, it's only
Yeah.
Well, you're still working at JPR?
I am, but very little. I'm 90 years old.
Yeah.
Just like the
Looking very sharp.
You can't really look right at it. I'm starting
No, I remember you. I remember your name. Yeah.
The reason we were in those days, we were talking about 10% rejected rate for higher than that,
It's very funny. If the rejection rate is more than 6 or 7, then people are starting to apply. Oh, shit. The chances are so low. And if it's 3 to 1, then it suddenly rises up back to 5 to 1.
You think it works?
It's 5 to 1. 5 to 1 is a sort of stable, if people think, well, but
That's underutilized.
yeah.
Not enough people applying to participate.
Yeah. 80% of the people participate.
Well, Sir Richard.
Yeah.
So nice.
Yeah, take care. Yeah.
Nice seeing you again.
Yeah.
I missed you from the year.
Oh, that's right. I knew you.
You want to know what kind of cheese? Mozzarella?
Oh, yeah. Nice to see you again. All right. Cameron, desperately. Oh, yeah, let me go.
Oh. This kid here. Oh, I saw him marathoning this morning when I was here. I want to talk about that.
Yeah, they can still do 100 kilometers.
All right. Thanks everyone for sticking around. We're going to get started with our Q&A panel. So over the next 45 minutes or so, we'll be happy to answer questions from all of you and our online audience on whatever astrophysical or astronomical topics that you have, be it questions related to the content of Richard's excellent presentation, or perhaps something that you read about in the news related to astronomy and space science, or something that you've just been confused about or want more information. We'll just start off briefly and have every member of the panel give a short introduction to who we are and the kind of science that we work on, and that might kind of prime the pump in terms of what you might want to ask us, because while we know some things, we don't know all the things, and we can try and work out some answers to your questions on a variety of different topics, but we're more likely to know more about the things that we have experience with. So I'm Cameron Hummels. I'm a research scientist here. I primarily work on galaxy evolution, much like what Richard is doing, but I'm more on the theoretical and computational modeling of galaxies, trying to understand, we're the ones who got it wrong, according to Richard's presentation in the very, very early universe, and the observations, the universe is constantly surprising us with, dodging our predictions for how it should behave according to what we think the laws of physics are. So I work on that. And mostly on kind of galactic atmospheres, the low density gas that surrounds galaxies. Emily?
Hi, I'm Emily. I'm a second year astronomy PhD student here. So I study collisions between massive clusters of galaxies. And these objects are really cool. So these collisions are extremely energetic. They're the most energetic phenomena in the universe after the Big Bang itself. And so that means they emit radiation across the entire electromagnetic spectrum. And so what I do is I use telescopes across the entire electromagnetic spectrum to observe these clusters. So things like radio telescopes, optical telescopes, X-ray telescopes. And then I run some simulations and I try to compare those simulations to the observations to understand the dynamics of these mergers. And once we've done that, we can place them in the broader context of the formation of structure in the universe as a function of time.
Yeah, my name is Dee or Delaney. I'm also a second year PhD student in astronomy here. And I also study galaxies. Again, I study them a little bit differently. So I am also trying to sort of form a census of what galaxies are going on in the universe, but I'm looking a little closer in than Richard is. I'm looking more around a redshift of 3. And around that time, the rate at which the universe was making stars, it peaks a little bit. And we're still not fully sure why that's happening. And again, that has implications for, structure formation and the whole mechanics of the universe as a whole. And the other difference between what I do and what you just heard about is a lot of the images you were just seeing, you were looking at the stars and the starlight in a galaxy in optical wavelengths or infrared wavelengths. I study galaxies in radio wavelengths, so extremely low energy photons, using a ground-based telescope at the Owens Valley Radio Observatory about 3 hours north of here. And I'm specifically looking at the gas that's just about to collapse into stars, molecular hydrogen gas. So it's like the fuel that will make the stars that you saw in the images up on the board.
Hi, I'm Kostov. I basically study the death of stars. So anything that goes boom in the sky, I'm excited by it. So we use this facility at the Palomar Mountains called the Zwicky Transient Facility. So it scans the night sky every night. And then it's like finding the difference game that we used to play earlier. So it's like we see a star as it is today, and I'd be looking at the same star tomorrow. And if we see a sudden rise in the brightness, I know that it has undergone an explosion called supernova. Also, like just a fun fact regarding this explosion of stars called supernova. So we know that the sun has been around for around 5 billion years, and it would be around for another 5 billion years. And the total amount of energy that it would emit in this 10 billion years, when a star goes supernova, it emits the same amount of energy in like a few seconds. Yep, I'll leave it at that.
You could give an introduction if you like, Richard. All right, are there questions from our audience members? I'll get to you in just a minute.
This question is for Richard. Now, you've had a long and illustrious career, and I know the views towards science communication have changed significantly. I know that in maybe the 60s, 70s, and 80s, science communication to the lay public was looked down upon. Even Carl Sagan sort of had to, deal with some pushback when he was in his efforts. Can you talk about the changes in philosophy in the area? Have they changed, or is there still room for improvement?
We're talking about public outreach
Yeah,
only?
public outreach.
Yeah. Well, now in both the UK and the US, it's a requirement of grant funding to dedicate a certain fraction of it to outreach, particularly to minorities and events like this, which is why we ought to, thank Cameron for setting up these kind of events. But yeah, it's interesting how even there's a story in my book about the the report that we wrote for the funding of the James Webb Space Telescope. It's a very nice book. You can get it online. It's called HST and Beyond, Hubble Space Telescope and Beyond. And there's a chapter in this that was written by an astronomer who chaired the panel, and it was called Taking the Public Along. The idea was that, just as I described tonight, it's an adventure, and the public should share that adventure and get inspired by science. And, we often get asked, why is astronomy important? And of course, it doesn't necessarily change breakfast or, remove poverty or cure diseases and so forth. But very recently, there was a study in the United States, actually, of all kinds of scientists and engineers, medical profession and so forth. And they asked them, when you were young, in your formative years, say 8 to 12, 14, what inspired you to switch to plan the career that you now have? And in many cases, it was astronomy, the curiosity about the universe. So, the value of these outreach events is particularly important in getting people to develop curiosity that enables them to have, think about bigger things. And that leads to careers that do influence society and lead to improvement. So anyway, this report, I had to present this report to the European Space Agency because this was a proposal that, James Webb was eventually going to be funded partly from Europe as well. And they thought this whole idea of outreach was, and this is what would this have been, maybe early 90s. Even in the early 90s, the guy interrupted my talk and said, please, Dr. Ellis, in Europe, we don't have this curious American passion for, we feel an obligation to talk about this in terms of public interest. So even in the space of 30 years in Europe, there's been a switch. I think it's clear that the US was the pioneer in this, in realizing the importance of accountability as well, of course, of taxpayers' money. But I don't know if others want to talk about, how outreach, shapes their own careers in America now.
I'm sure Cameron has thoughts, but while
I
he's
have
walking
thoughts,
over,
but please.
yeah. I don't know, you will hear from a lot of people as you're learning a subject that you don't really understand the subject until you can teach the subject. And I think that, the way I've been able to measure even what I've learned over the past few years in graduate school for me has been my ability to explain a concept when asked a question in a setting like this. And so I think it's critical for just cementing your knowledge and then sort of understanding how different concepts link together and what might confuse people, what might be confusing you. And so just as a learning tool for someone who is trying to learn astronomy professionally, it's very helpful.
I'm just going to add on to that, and then we'll get to questions. I agree both with Richard and Dee on this, and I think there has largely been a generational shift. It's no surprise that much of our panel here is composed of junior scientists, and I find that oftentimes there's a much more of a bent on willingness to contribute the science that they've done back to the public by junior scientists. There's a little bit less of that at the senior level. Of course, there are exceptions like Richard here. But in general, there's a bit of a bias because people who go on to esteemed research faculty or teaching faculty positions are usually the ones who spend a lot of their time on the science results itself and less perhaps on taking that and putting it in a nice pedagogical form that's appropriate for a larger audience. And so I think historically there's been a bit of this direction where more senior people are less inclined to be involved in this, but I'm hopeful that that's changing, and I think that it is with the current, the last 10 or 20 years. The question from this gentleman, and then we'll get to some of the other questions as well as some of the online questions.
Thank you very much. It was fascinating, to say the least. I've had a career in business and no astronomer, but this is the query in my mind from the general public, so to say. The universe exists in human consciousness. Now, all the work that you have done, does the universe have its own consciousness?
So does the universe have its own consciousness? It's a challenging question. There are a lot of things that we don't understand about the world around us and nature. I don't think other panelists can speak for themselves as well and chime in, but I don't think there's been a lot of hypotheses from physical scientists about a potential for an underlying consciousness that ties everything together. Of course, science fiction and philosophy speculate on this, like the idea of the Force from the Star Wars themes or something like that. But I don't think yet that there's, we're struggling to identify the physical laws that dictate how things behave. And I don't think we yet have the capability of identifying anything more subtle than that if it were to exist. So it's kind of outside of our region of theory at this point. Do you guys have anything else to add on that?
It relates to the question of whether the universe has a purpose. Would that be closer to your question?
Yeah, yes.
And
or is this just a random event?
Well, it relates to, maybe we should turn the question around and say, do we ever, we think very deeply about what we're doing, all of us when we're doing our research. Of course, we don't think about it every day. We come into work and, there's the humdrum of getting observations or running computer models and everything. But every now and again, we do sit down and think, what is all this about? And where did it come from? And what's the purpose of all of this? And so I think, you could get 10 astronomers here and they'd all give different answers, about, do you believe in God? Do you think that some supreme being kicked it all off? And if you do you think that there's just sort of waiting and watching to see, is it an experiment? And all these kind of things that many people have written books about. I don't think we all agree on, what's the purpose of the universe. And so that you get you'll get a range of answers, I think.
Do you have any personal conviction?
No, I was brought up religiously. My grandfather was a minister, a Baptist minister, and he died giving a sermon in the pulpit kind of thing. But so I was brought up in a very religious family. But I'm, I can imagine a God that set things going, but I wouldn't say the evidence for an interactive God is very strong.
But there certainly are, as Richard points out, there are a lot of astronomers who are spiritual and religious and tie in their scientific research into philosophy and religious perspectives on the purpose of the universe. But yeah, I largely fall in the camp that Richard described as well. I'm primarily an agnostic in terms of spiritual beliefs. Do you guys want to add on, or? Okay, just feel free to chime in whenever you want. Yes.
Hi, sorry, I've been a little bit impatient, but I'm sure this is always important, but can we, since we have a limited time here, can we actually get back to the elephant, which is that graph? And we were talking about the question, so there's luminosity versus redshift, and the predicted relation is logarithmic, but seems like observed relation so far is linear. So the question is that because universe is not expanding exponentially, or is that because somehow galaxies have different dynamics than we knew before?
Excellent questions. Well, we were just discussing this at a research meeting earlier this week about what are interpretations of why galaxies might be brighter in the early universe than we expected them to be. And there's a variety of different things that could be at play, and perhaps even more that we haven't yet considered. But feel free to chime in here. Okay. So one of the issues is that in current galaxies at the present day, kind of in nearby locations, so at the present universe, we reasonably well understand the interaction and how you'll have a burst of star formation that allows stars to be born and then they shine their light outward, and how that can't continue on sustained for a long period of time for reasons that tie into things like what Kaustov does his research on, which is to say, some of the most massive population or most massive stars in that population will turn into supernovae. They'll blow up and they'll kick out the rest of the gas in the vicinity that would later, without that explosion, otherwise go on to become more stars, like the fuel for new generations of stars. This is known as stellar feedback because it feeds back on the fueling of new generations of stars and prevents those, at least temporarily, in that vicinity. And so we think that you can either have a very low kind of sustained rate of star formation where you don't have a lot of these explosions, or if you do have a bunch of stars that are born, the consequent explosions of gas will blow out and quench the star formation of the next generation until sufficient time has passed to allow this gas to fall back in. And when we look at the generations of stars across the universe, we kind of have made predictions based on our intuition from the generations of stars that are going on here. But it does, perhaps stellar feedback behaves in a different manner in the very distant universe, when the universe was much younger and those galaxies were much younger in their formation, that allows them to kind of proceed and build up these stars unstopped by supernovae feedback or stellar feedback that might quench those star formation events and allow it to, build up much faster than we can here. That's one potential explanation.
Still supporting evidence towards the universe expanding exponentially.
Is there still supporting evidence for the expansion of the universe that's accelerating?
Accelerated expansion. So that's why you more inclined towards just different galaxy dynamics that we don't understand.
Well, that's certainly true. And the universe, because the universe is expanding, it means that in the early universe, things were denser, things were closer together. So you tended to have more interaction between different galactic bodies. You tended to have an overall higher density. You tended to have a variety of different changes with the environment that aren't present here. And we're only kind of starting to be able to probe that observationally to put that into our models and better understand the interactions.
Let me try and explain the problem again, and also give an alternative explanation in addition to what Cameron has said. So what we're finding with James Webb is that the galaxies are converting their gas into stars more efficiently than they do at later times and in the local universe. Now, what that means is that as the gas clouds collapse, they produce brighter stars. And so here's the problem that we're trying to understand. Locally, when a gas cloud collapses, it forms maybe 1,000 stars, okay? And these stars have a range of masses. So they range from feeble stars that are 1/10 of the mass of the sun, up to stars that are 50 times the mass of the sun. And as I explained, the stars that are 50 times the mass of the sun shine very, very brightly. And the stars that are 1/10 the mass of the sun are really feeble little things. It seems that this distribution of masses of stars is universal. Well, we assume it is. So wherever we go, a gas cloud fragments, and there's always this range of masses, a few very massive ones and a lot of little feeble ones, okay? And this is sometimes called the initial mass function. Now, when we go to the early universe, the composition of the gas is pristine. It doesn't have all these heavy elements. And so there are theories, including ones that Cameron works on, where it's thought that in the early universe, this distribution of stars is skewed to more massive ones. Instead of a mass limit of 50 times the mass of the sun, maybe in the early universe, there are whopping stars that are 300 times the mass of the sun. They're going to shine very, very, very brightly, but for a very short period of time because they burn their fuel up very, very quickly. So one explanation of this inconsistency in James Webb is that we're witnessing this early period where the chemistry is very pristine and it's producing many more supermassive stars. And it's going to be hard to prove. You may ask, well, can't you find out? And the answer is we can't at the moment. We need to get high quality spectra to see the signatures of these very, very supermassive stars. And I think that will come with James Webb. It certainly has the sensitivity to do it. So, you know, give us time to figure out what's going on. But at the moment, it's big business.
Yeah, the one other sort of consideration for this too is that these are objects that are really, really far away, and this is light that has traveled a really long time to get to us. And as light travels, it sort of spreads out, and so it gets fainter and fainter. And so, like, it required this massive space telescope to actually see these objects. And even then, it's only seeing the very brightest objects. And so there is maybe also an issue where these are just really unique things, or we only have like 10 or 20 of them that are confirmed. It could totally just be that those are the ones that look like the ones that we see today, so we recognize them as galaxies first. And also, like, our tracers for studying how stars are made, those also depend on the universe around us, which has the chemical composition that we know and understand. So that's something that, you know, astronomers are constantly thinking about and trying to correct for, but there's really only so much you can do. You need the light in order to understand what the object is, and the light needs to get to you, and you need to be able to collect it and recognize it as an object in the first place. And so there's some selection bias as well that might be playing into this.
That ties into a question that we had from our online audience. I want to make sure we do this justice as well. The Nerdy Walker asks, how long after star formation began did the first galaxies form? Has the James Webb Space Telescope given us any new insights on this? So really tying into the questions that we've just been discussing, you know, when is it predicted that those first stars formed that didn't have any of these heavier elements present at all? They just had the hydrogen and the helium present, which gives certain different dynamics in how stars form and could potentially produce these supermassive stars. So how long is the period between these first stars forming and when the first galaxies are predicted to form? And also, yeah, do we have a hope of being able to see with James Webb or future instruments be able to see the formation of these first stars? That's a challenging question. Various different models predict those first stars as forming somewhere on the order of, I think POP3 stars form at redshift of 20 to 30. And you saw from Richard's outdated plot, although you did have the up-to-date, later you had the up-to-date. So the highest redshift galaxy that we've so far identified was redshift 14. Okay, 14, which is about 200 million years, 300, forgive me. 300 million years after the formation of the universe, after the Big Bang.
But there is, I mean, the question, you know, is often asked, did stars form before galaxies? Is it possible that a single star could form by itself even earlier, explode and then disappear, and, you know, or, you know, did the first starlight emerge in systems like clusters of stars? And it all depends on how these gas clouds fragment. So as a gas cloud collapses, the simulations suggest it breaks into inhomogeneities, and these inhomogeneities then create many stars all at once, okay? A cluster of stars. But, you know, there was some discussion, and Cameron's probably much more of an expert on this than me. There was originally some ideas that in the very early universe, say redshift 30 or 40, this fragmentation might not happen, and you could get directly to a giant star, you know, which would be, I don't know, 1,000 times the mass of the sun or something, and it would fizzle out very, very quickly. And only when, this fragmentation started to kick in would you get clusters of stars and galaxies. The sad thing is that I don't think James Webb has the sensitivity to test the detection of individual stars at redshifts 30 or 40.
I don't think so.
It only has the capability of detecting clusters of stars like, baby galaxies. So I don't know what's the story now with fragmentation in the early universe.
So this isn't a field that I directly work on, but I'm somewhat familiar with the content of this field. One thing that we do have a better handle on is these ideas where you have, so as Richard has mentioned, you form stars out of large clouds of gas that become gravitationally bound to each other, and it slowly collapses. And then in the present day universe, it fragments into individual chunks, and you kind of have a batch of stars that are all born roughly simultaneously. Not truly simultaneously, but roughly simultaneously. Whereas in the high redshift universe, that may not be possible. One area that this ties into as well is the formation of supermassive black holes. So as has been witnessed, particularly with the James Webb Space Telescope, we've started seeing galaxies on the other side of the universe at very early times that have evidence for very massive black holes in their centers. And right now, we don't have a lot of good methods for creating these supermassive black holes in such a short period of time after the formation of the universe. Because when we see supermassive black holes today, or even stellar mass black holes, like masses on scale with our own sun, it takes a long time for them to merge together, simply because the dissipation of energy that allows them to eventually spiral in is very low through gravitational wave ejection, like what was discovered with the LIGO instrument, or emission, like interactions from their accretion disks. This takes a very, very long time. And if you were to take two to three solar mass black holes and merge them together every, I don't remember the exact time scale, but it's on the order of hundreds of thousands, millions of years, it takes a long time to build up your supermassive black hole that's in the center of a galaxy that's 1 million or 1 billion times the mass of the sun. And so how this ties in, I'm not just going off on left field here, how this ties in is that there are models for, if you have a collection of gas that's large enough, massive enough, that might be 1,000, 10,000, 1 million times the mass of the sun, and because it's devoid of these heavier elements that can allow cooling to occur quickly, so this will start to fragment into the individual star chunks. If you keep that kind of irradiated with some other energy source, you can allow that to essentially get massive enough that when it does start to collapse, it collapses down into a single object. And if that single object is very massive, 1,000 or 10,000 or 100,000 times the mass of the sun, then no other forces can oppose gravity, and they will collapse into a black hole. So there are areas that are in very active research in terms of trying to identify the different ways in which gas clouds will collapse under their own gravity in the early universe and potentially form the first generations of stars, which may be massive, more massive than we have here, or supermassive black holes, known as the direct collapse method for forming these supermassive black holes. But it's definitely an area that a lot of people are working on and is not figured out all the way. Sorry, that was very long-winded. Didn't mean to take up that much time. Yeah.
So this is more of a process, a research process, and also maybe somewhat political, of how do you, especially as a theorist, like you say, you may be working down a theory, you may be going on a process, you've got your things written, and now all of a sudden everything's invalidated. How do you pivot? How do you start all over? Do you just say, well, during periods of such extreme discovery, what's going on from the experimental side? And it may also be from the experimental side. What if you set up your experiment, test one thing, but now there's something much more interesting that you want to experiment on? So how do you change your observation request or something like that? Yeah. Okay.
There's a joke in my book. If you buy my book, there's a very famous theoretical astronomer that was in my university. He's very famous, Carlos Frank. And one day, I told him. He asked me if I could do something the following week, and I said no. I said I'm going observing next week. I won't be here. And he said, well, what are you going observing for? And I said, well, I'm going to do this, this, and this. And he said, that's a complete waste of time. He said, I already know the answer to that question. So firstly, observers, generally speaking, especially me, don't go to telescopes, with a theoretical checklist, A lot of it is, and I think you should chime in here. A lot of it is exploration. There are so many phenomena, especially variable phenomena in the universe that we don't understand, that it's sometimes better to just go out there and say, what's out there? Let's just go and search. Now, when theorists fail to predict what the observation is, I'm going to hand over to Cameron. So what do you do when you see a result?
So what do we do when we find a result and it disagrees with what our predictions are? Well, so to directly answer your question, do we have to throw out everything? I have two main things to comment on. One, usually all the work that you've done isn't for naught. There are other applications of the techniques that you may have involved, or the science, if you did the science in a firm methodology and such, that you can apply it to other fields of science. So a lot of scientists, I feel like, they develop a tool, whether it's a piece of software or whether it's an analytic methodology, and then they have their hammer and they go around the field of science and look for nails, look for particular problems that they can apply that particular code or technique against. So there's lots of opportunities in that front, but there's also, I think there's a really key point that scientists shouldn't be too involved with their own hypotheses. I think this gets us into trouble. So if you propose a hypothesis that perhaps galaxies formed at this redshift, and that is what we think by theory, and then that turns out not to be true, or there's observations that suggest that perhaps that's not true, I think it's important to take into account the new observations and reevaluate the validity of the hypothesis that you formed in the first place. Because I think we get into problems when people don't do that and they become so tied up in it, whether with their own identity or their own theories about how the universe exists, in conflict with the actual evidence out there. And that, yeah, I think that's really against the scientific method. So constantly taking in new data and allowing that to modify your view of the world and modify your hypotheses and your theories. Yeah, please, Kesta, or Emily.
Oh, I was just going to add on that a lot of times you start with this grand idea for a project and you decide, oh, I'm going to spend the next 3 years investigating this because this is how I think it should behave. And, in the process of doing that, you hit hurdles, you have to develop new tools, new techniques to analyze these things, and you also run into new and exciting things. So you can start something and 6 months later, you go down a rabbit hole that lasts you another 2 years and extends your project timeline. So you're deferring the original thing you're testing, but you're learning a lot in the process. And I think that's a lot of what science is about, is we have these things that we're testing, and yes, those are the objective or the grand goal is to come up with a definitive conclusion on that, but you learn so much in the process that sparks, creativity for other people who might see that work in the process and think, oh, wow, that's really cool. I'm now going to test that hypothesis for them as well. And that's how science sort of, grows like that. And so it's important to keep the overall objectives in mind, but also to be curious. And I think that's something that scientists should really strive to do.
I think the universe does not necessarily need to behave the way we expect it to. So the reality is what it is, and then our interpretation is separate from that. And coming to the observational point of view of your question, I think often what we decide to observe or our big projects are based on or driven by technology. For example, when Richard talked about CCDs in his talk, that enable a lot of new science that could possibly be done. For example, we were just talking about in today's journal club where imaging could be done with readouts of a few microseconds even. First you have a technology that enables you to do that. And then once you go out into the universe with that new technology, you'll always be finding that the universe has something for you in place.
Thank you for these answers. Can we take that question? And these are probably all very important, but can we just take that question and narrow down it to a little bit more specific, meaning that all is true, yeah, sure, but we have James Webb Telescope, and there's a limited time on it, and proposals get approved somehow. So there's a certain consensus in communities that we as a public don't know, that it's guys as an insider information because you go to conferences. So I think the real question is like, what is generic, since there's still discrepancy over the explanation of like what theory predicts versus observation. So certain types of proposals gets approved more than the others. So the question is, what is the general consensus in the community right now over what type of observation is the most promising or valuable over the next like 10 to 20 years? Generic stuff, not really that valuable. People can read it online, but something that's you currently discussing in the community on the conferences that you attended, for example, is what's interesting. Thank you.
Well, I think Richard mentioned specifically one of the key things, at least in observational cosmology, that we're trying to look at, which is why is there this discrepancy in terms of the predicted brightness from distant galaxies on the other side of the universe? Or are there observational consequences of this direct collapse method for forming either a black hole or a star at very early times? In terms of other things, I mean, I don't sit on the JWST, so I don't get to evaluate the different telescope proposals. But
I think overall the community is intelligent and very receptive. The time allocation committee is always interested in new ideas, and it doesn't stamp down. It's not as if there's a conservatism in the community that new ideas are not welcome. It's also, you know, when I showed that discrepancy at the end of my talk, it's very important, as somebody asked me, I think, to realize this is really early days. You know, it's amazing what James Webb has done, but, you know, we've got 15 years of hopefully of observations. We're going to learn a lot more as we start to probe bigger areas, go deeper, get better spectra and so forth. And there will be surprises. And I think what the wonderful thing I've learned during my career is that these observatories always deliver surprises. It's not like the questions we ask today will be the only ones that James Webb asks or answers, okay? There's going to be surprises along the way. And that's what's so fantastic about science, is it's a roller coaster. You know, you wake up on Monday and you think by Wednesday you'll be doing this and the other, and then suddenly something appears on the internet that makes you think, my God, you know, what I thought on Monday is not correct, and I'm going to have to rethink, and that's changed my view. And the community is flexible. The time allocation committees are sensible, generally speaking. And it's just, you know, I don't think there's this fear that, you know, wacky ideas are rejected, and, you know, I think there's freedom in the system. Young people agree.
Yeah, I don't know particularly about JWST, but then I would guess it's the same for all telescopes. So, of course, the first thing that I would be giving highest priority to would be what is the science result that you could derive out of those telescope time. I mean, every minute on a telescope is like, it actually costs money. And then what's the science result that you expect out of it? That's number one. Number two, of course, would be how feasible is it? With that amount of time, can I actually get the science done? So that's the second thing that I would, I think, look at. And I think the third thing would be, just in terms of looking at the science result, it could be two things. Either we try to improve upon a previous known thing. For example, earlier I had 1,000 galaxies redshift information, but with this new program, I'll have probably 1 million galaxies redshift. How much would that contribute to new science? So that's, I think, one thing. And the second, of course, would be, which I answered previously, which is looking for entirely new phase space, where we are like open to surprises.
So there's a question from our online audience. Coco Oates asks, in my astronomy class last night, we discussed the galaxies James Webb is finding. Do you think as Webb progresses and more observations are taken, the Big Bang theory itself will be challenged? It's interesting. I've heard this kind of thrown around in terms of in talking with people, not usually scientists, usually people who are curious about the science. And so right now, you know, just so sure, to make sure we're all on the same page, the Big Bang Theory is kind of the most popular view of how the universe has progressed over time. And probably most of you are familiar with the main idea, which is in some sort of Big Bang that we don't well understand. There was a dramatic, that was kind of the beginning, not the dawn, as Richard was talking about in his presentation, but the beginning of that space-time, and it's been expanding ever since. And we now know that it's actually accelerating in its expansion. And yeah, you gave this wonderful early in your presentation, you described how there were the dark ages and the formation of structure, and then stars and galaxies and so on and so forth. The Big Bang was only really accepted as the most popular way of interpreting the results from the world around us in the early, early middle part of the 60s. Okay, I guess the first piece, CMB, sure. The first piece of evidence for it was the expansion of the universe, which was discovered by Hubble and collaborators in late 1920s, early 1930s, then the cosmic microwave background and trace elements of
it's held up remarkably well.
Yeah.
You know, there have been so many attempts to dethrone the Big Bang Theory. So, you know, there were, even after Hubble and Hubble's data and other astronomers like Slipher, you know, provided evidence for the expansion of the universe and hence a beginning. You know, famous theorists like Fred Hoyle, you know, refused to accept it and for the rest of his life. And then the microwave background, which is the glow from the Big Bang, was serendipitously detected in 1965. And people love, you know, it's always great fun to topple the standard theory, you know, and the media loves, you know, to find out, you know, recent observations suggest a major rethink of our understanding of the universe. So the result that were very recently from James Webb that triggered something like this was a paper from Australia, which suggested that at a redshift of 10, the galaxies were too big, too massive, not too luminous, but too massive to have been able to have formed in the short time since the Big Bang. And this got a lot of publicity. And at the conferences that I have attended, there's been great skepticism. And so other groups have looked at this data and they've concluded that these masses were significantly overestimated by the Australian group, maybe by a factor of about 40. And so, you know, I think at the moment, you know, there's no evidence from the James Webb data that we should throw away the Big Bang. That doesn't mean that there aren't puzzles. Just because there's a puzzle in astronomy doesn't mean you have to destroy the whole empire. You know what I mean?
Indeed. A good example of that is Newtonian gravitation. Newton came up with the idea of universal gravitation and how it governs things here on Earth as well as in space. And that held up. And then Einstein, in a way, dethroned it, but really enhanced it to take into account additional observations. And now we have the theory of relativity, which is mostly in agreement with Newton, but it's a little bit more enhanced in regions of very massive structures or close proximity to massive structures. So I don't think that the Big Bang is going to be thrown out wholesale, but certainly there may be modifications to the theory as we understand it today. Okay. Additional questions? I can ask another from our online audience, and then we'll probably finish up in the next 5 minutes. But if there's any here, okay. Let's see. Oh man, there's some good questions here. How about, what role did dark matter play in the early galaxies that are being observed with the James Webb Space Telescope? Let's first just make sure everybody's on the same page with respect to dark matter. So dark matter, as Richard discussed in his presentation, gives it an air of mystery because we don't fully understand it. And it's true that we don't, but we do believe that its presence is required to allow objects to to move and change in the way that they do and form in the way that they do. But there seems to be this unseen matter that we can't observe with telescopes of any particular portion of the electromagnetic spectrum, whether it's optical or infrared or UV or X-ray. There's some matter that's operating and not interacting with that material that is responsible for holding galaxies together, essentially, because they have so much mass that they have a lot of gravity that binds these things together. And in some cases by factors of 10 or 100 or 1,000 times more than the matter that makes all of us up, protons and electrons and other luminous matter. So does dark matter, so getting to the question then, does dark matter actually play a role in a different way in the early universe than it does at present day in the formations of galaxies? And I have to think about that. You, please.
Well, the answer is yes, it does. So what happens is we think the dark matter is not the stuff that makes up you and me, but is some elementary particle. And this elementary particle, which sadly has not yet been detected by the particle physicists, it detaches from the expansion of the universe at an earlier time. So before the hydrogen clouds are there, even before the hydrogen atom forms, the dark matter has done its own thing and has clustered together into nuggets of dark matter. So when finally the hydrogen clouds form, they're drawn into the nuggets, and this gives them a head start in growing. And if we didn't have dark matter, then these gas clouds would not collapse as quickly as they do. So in fact, you know, if we didn't have dark matter, we wouldn't be here, because it would take so much longer for the hydrogen clouds and the galaxies to collapse. And so the dark matter is an essential ingredient, and it's just so frustrating that we don't know what it is. But we know it's there. What the astronomer can do, the astronomer can't really tell what is the dark matter. That's really the particle physicist's job. But what the astronomer can do is measure how much there is and where it is. And that lensing, I showed you this beautiful, these swirling arcs and so forth. We can use that technique to make maps of the dark matter. And we know where the dark matter is, and we know how much there is. We just damn well don't know what it is.
The other thing about dark matter is it's something that when you hear about it, it seems really exotic and cool and scary, which it absolutely is. But from the point of view of someone who's doing theory or trying to understand how galaxies evolve, it's really predictable. Basically just gravity works on it, and that's about it. Nothing else seems to affect it. Whereas the matter that we can see is really messy and really weird, and the chemistry changes things, the light changes things. So it's actually simpler, yeah. So it's probably more likely that the weird stuff happening at high redshift that we're starting to look into with Webb is weird stuff happening with more mundane, everyday matter that we can actually interact with, and not with dark matter itself. Dark matter, we have a pretty good handle on how it behaves. We just don't know what it is.
I can just add a line to it. I think to solve any mystery in science, I think it's always a good practice to start with the more simpler explanations before going to the more exotic ones. So probably I think a step-by-step explanation for this could be, first you look at whether the data is believable. You try to confirm the photometric redshift, which is spectroscopic redshifts. Then you move on to more simple, a bit more higher end explanations, but then still possible. Like, do we really understand population 3 stars? Could they be really powering what we see? Then if we prove the confirmation that that's not being able to explain what we see, then we move on to more exotic things like whether dark energy model needs to change, or whether the dark energy, the rate at which the early universe expands itself, needs to change. So I think it's usually a very good practice in science to start with the more simpler things and then gradually move on to the more exotic explanations.
Totally agree with that sentiment. All right, that brings us to 10 o'clock. Thank you all for joining us. Thank you, please, a round of applause for our speaker and our panelists. Excellent work, team. Thank you all for sticking around. Again, we do these once a month. Our next one, I forget the exact date, it will be given by Nitika Yadlapalli, who is a finishing PhD student here, talking all about a radio telescope that she's built at the Owens Valley Radio Observatory just a few hours north of here called Sprite, the kind of science that can be done with that, as well as just what the process of like how radio telescopes work and what the process of building them is like. Hopefully we'll have better luck with the clouds and able to observe things in the sky with our telescopes, but stay tuned. And our next Astronomy on Tap, again, will feature discussions of the cosmic web and the distribution of matter on very large scales by a JPL scientist, Leonidas Moustakas, as well as a Caltech scientist, Sofia Gallego. So thank you all for your time. And remember, the book is available, Princeton Press, 30% off. The description is online and on our website. Thanks, everybody.
Thank you so much.
Cameron, how do we get the discount?
I'll get it to you now.
Ellis 30.
Ellis 30. I can give it to you now.